Sorry I'm late, class. I was trying to finish up writing an email and it just took more time than I thought it was going to take. I will get started in a moment here. I'm watching the viewer count go up. I'm going to start once I hit 20 viewers. Ooh, brother. Just one of those days today. All right, I'm going to go ahead and get started as I hit 20 viewers. Let me zoom this in. So, let's just talk really briefly about what we learned last time. Last time, because that was a pretty important lesson, last time we learned about simple harmonic motion. Which I will talk about as SHM, just because simple harmonic motion is a lot of syllables. And so simple harmonic motion means that your position time graph has the form, your position as a function of time has the form a cosine of omega t plus a constant. Okay? And so if you have a position time graph, your position time graph looks like a sine or a cosine. So it's going to be, I don't know, something like this. Like that. Okay. And so we can see that this oscillation, this position as a function of time, it has a center line, which is right here. And so that center line is the value C right here. So this is C. Okay. Now, the distance that the object strays from that center line, by the way, the center line is also called the equilibrium position. Okay. So the distance that it strays from that center line is called the amplitude. So we can understand the amplitude and the equilibrium position both in terms of the equation and in terms of the graph. So that is important. You should be able to see the equation and identify the amplitude. You should be able to see the graph and identify the amplitude. And then we also have the period, which is denoted by T. Okay. And the period is the time it takes to complete a full vibration. So if something is going in simple harmonic motion, it's going back and forth and back and forth, back and forth and back and forth. So the time to go back and forth is one period. So sometimes students think that one period is just from here to here, but it's back and forth is a full period in simple harmonic motion. Okay. So the period does not appear in this equation, but this Greek letter omega is related to the period through period is 2 pi over omega. Okay. So there you have it. So there's an equation that results in simple harmonic motion, and that equation is negative omega squared x times x minus c, I should say, equals the acceleration. Okay? So this is the equation that will result in simple harmonic motion. So we are going to, what today's lesson is about is we are going to study simple harmonic motion systems. And in particular, we're going to study two of them. So the first system that we are going to study is called the mass spring system. Okay, so what does a mass spring system look like? Well, you have a, here's a wall, and then here's the floor. The floor is going to be completely frictionless, okay? So this has mu equals 0. The coefficient of friction is 0. We have a block of mass m, okay, which is sitting on this surface. So because it's a frictionless surface, if you tapped it and made it start moving to the side, it would just continue sliding forever because there would be no force to stop it. But what we do instead is we attach a spring to it. The spring has a stiffness K. All right? And so I'm going to call this x equals 0. Look at this class. I just have they're just like two dogs. Just out. Hazel in particular is just out. I messed up my wires. Okay, so I don't know why my document camera is so laggy today for some reason. So if you were to take this mass and you were to pull it to the right, that's going to stretch the spring, and the spring is going to react by pulling back to the left, okay? If you were to take this mass and push it to the left, okay, if you were to push it to the left, that's going to compress the spring, and springs don't like being compressed just as much as they don't like being stretched, so it's going to push back. So we can see that if you were to pull this mass and release it, it's going to go back and forth. So this system will undergo simple harmonic motion. So let's go ahead and see if we can get the period of that simple harmonic motion. Okay? So we're going to start out with Newton's second law, which says that net force equals ma. All right. And then what is the force? The force that's causing the motion is the elastic force. All right. So the formula for the elastic force is Kx. And an important thing here is that there's a minus sign. So why is there a minus sign? Well, we saw that if I stretch this mass to the right so that x is positive, so this is positive x and this is negative x, we can see that if we pull the mass to the right so that x is positive, the spring is going to be stretched so that the force is negative. So a positive x results in a negative force. Okay? So then what I'm going to do is I'm going to divide both sides by m. So we have minus k over m times x equals a. All right? So at this point, what we want to do is we want to compare it to the defining equation of simple harmonic motion, which was minus omega squared x minus c equals a. All right. And actually, we could write it as x minus 0 in this line, just to make it clear. So this is, I'm going to actually rewrite this. So rewriting this, negative k over m times the quantity x minus 0 equals a. All right. So now let's compare. Let's compare these two. All right. So by comparing the equation for the mass spring system with the defining equation of simple harmonic motion, I can see that the two equations are the same with, so we can see that c equals 0. Okay. And then I can see that omega squared is k over m. All right. So this is actually going to tell us what the period of the simple harmonic motion will be. Okay. So if we take the square root of that, we get omega is square root of k over m. Okay. Which then says that the period is 2 pi over omega, which would be, now if you invert root k over m, we get root m over k. All right. So we have 2 pi square root of m over k. All right. And that is the period of the mass spring system. So this is one of our two main equations today. All right. So I'm going to actually copy this over to the other side of the page. Okay. So so now we're just going to make some observations about this equation. Okay. So the first observation that I want to make is that this equation basically behaves exactly like we would expect it to behave. What if you had an extremely heavy mass that is attached to this spring? you can imagine if you had an extremely heavy mass and the spring is trying to move it around, it's going to go really slowly. It's just going to be like, it's going to take a long time to go back and forth if it's heavy, okay? And notice how we see mass on the numerator. So because mass is on the numerator, as the mass gets bigger, it takes more time to go back and forth. That's just what we expect, okay? So basically, as the mass goes up, the period also goes up as expected. All right? So our everyday experience with springs and the way things behave, we always want to remember in physics, the equations have to match reality. Okay? Because physics is an experimental science. Okay? So if this equation doesn't match reality, then it's useless. All right? The other thing we see is that as K increases, we can see that K is on the denominator. So as K increases, the period is going to go down, which also makes perfect sense, okay? Because if you have a really stiff spring, a really strong spring is going to be able to whip a mass back and forth in a very small amount of time, okay? So this is also as we expect. But there are a couple of things about this equation that you might not expect, okay? So in particular, we can see that the amplitude does not appear in this equation, okay? So what that means is that the period does not depend on amplitude. And I'm going to put an exclamation point there. The period does not depend on amplitude. So in other words, it doesn't matter if you pull the mass a little bit to the side and release it, or if you pull the mass a huge amount to the side and release it. It's going to take the same amount of time to go back and forth. So that might be a little bit counterintuitive. And the reason is that if you pull the mass further back before releasing it, it has a longer distance to travel, okay? But the more we stretch it, there are greater forces involved, which means that it's going to build up more speed as it goes back and forth. And so basically, the greater distance resulting from a larger amplitude is countered by greater speeds. Okay, and so they compensate each other exactly. Okay, so the period does not depend on the amplitude. Okay. And another thing I want to point out is we could have what's called a vertical mass spring system. So a vertical mass spring system is one where you attach this, basically you're hanging this, if we were in class, this was the experiment that we would do. We would actually hang a mass from a rubber band, but you would have some kind of a spring, and here's the mass, here's the spring. So that's a vertical mass spring system. Now, maybe the mass spring system looks like this on Earth. Okay, if you were to take this same mass spring system and move it over to Jupiter, where the gravity is twice as strong, what you would find is that the mass is now going to dangle down here, right? If you were to take this vertical mass spring system to the moon, where gravity is 1/6 of what it is on Earth, it would be like this. And so there are a couple of things about vertical mass spring systems. So for vertical mass spring systems, first of all, the equation for period is the same. Okay, so it doesn't matter. It's still, the equation is still 2 pi square root of m over k for the period, even if it's hanging vertically versus if it's horizontally. I'm not going to prove that to you, but it is possible to show that that is the case. And furthermore, if you have a vertical mass spring system, the period does not depend on gravity, which might seem, again, counterintuitive. So if you take a vertical mass spring system, it's going to have the same period on Earth that it has on Jupiter, that it has on the moon, that it has on any other astronomical body. The difference is that depending on the gravity, the equilibrium position changes. So here we have an equilibrium position for Earth that's right here. But the stronger the gravity is, the lower the equilibrium position is going to be. Okay. But the equilibrium position shifts. So the period does not depend on the amount of gravity, but the equilibrium position does depend on the amount of gravity. Okay? So we're going to be studying the mass spring system a lot more in next week, but I just wanted to show you this equation for today. And then there's a second simple harmonic motion system that I want to study, which is called the simple pendulum. Okay, and the simple pendulum is basically a string. The string has a length, which we will call L, and then at the end of the string, there is a mass, which has size m. So that's called the pendulum bob. Okay, and this mass is going to swing back and forth. So like you're trying to hypnotize someone. Okay, it's just going back and forth and back and forth. Remember, a period is all the way across and then all the way back. Okay. So to prove the equation for the period of a simple pendulum is a little bit beyond the scope of this course, but you do need to know what the equation is. And so the period of the simple pendulum, the equation is 2 pi square root of the length of the pendulum divided by the acceleration due to gravity. Okay? So now let's make some observations about this equation. So maybe some of you have been to Griffith Observatory before. And if you go to Griffith Observatory, you have a, right at the entrance, or once you go inside, right when you go inside, there's a Foucault pendulum, okay? And the Foucault pendulum is an example of a simple pendulum, and it has this really long string that goes down from the ceiling almost into a pit and almost touches the bottom of the pit, and it's just swinging back and forth. And one of the things you'll notice is that it takes a really long time for that pendulum to go back and forth. So long pendulums take a long time to go back and forth, okay? And that's what this equation says. This equation says that as the length increases, the period increases. Why does this equation say that? It's because length is on the numerator of this fraction, okay? So this is as expected, okay? So, and to remind you, I would say, remember Griffith Observatory, remember that giant Foucault pendulum at Griffith Observatory. A Foucault pendulum is one that is, the pendulum, it knocks over dominoes basically as it's swinging. A Foucault pendulum is one that is designed to demonstrate the fact that the Earth is spinning. So what that pendulum is doing is the pendulum is keeping the same plane of rotation, and the Earth is rotating underneath it. And so basically a domino. So the pendulum is keeping the same orientation, but then the Earth rotates and it moves a domino into the path of the pendulum and knocks it over. Okay? So that's what a Foucault pendulum is compared to a regular pendulum. It's just specifically designed to demonstrate that fact. And the other thing we can see is that the acceleration due to gravity is on the denominator. So as gravity gets stronger, it actually takes less time to go back and forth. And that makes sense, because if gravity pulls this thing down faster, it's gonna obviously take less time to go back and forth. Okay. So now we're just going to make similar observations. Again, the period does not depend on amplitude for the same reason as in the mass spring system. Now, amplitude of a pendulum is kind of like how big is the swing. So big amplitude is like this, small amplitude is like this. Okay? So the period does not depend on amplitude. Okay? So that is a major point. And it's for the same reason, okay? If you do a bigger amplitude, the swing is a greater distance, but you build up more speed, and it ends up taking the same amount of time. Okay? The other thing I want to point out is that the period does not depend on the mass. Okay? The period does not depend on the mass. So a heavy pendulum bob is going to take exactly the same amount of time to go back and forth as a light pendulum bob. But here's the thing. you can imagine in a real physical situation, the pendulum bob is going back and forth, and eventually it stops. Eventually it settles down, and it's just like this. The more massive your pendulum bob is, the less susceptible to air resistance it is because it has more inertia, and so it's able to go a lot longer before stopping. Okay, so the Griffith Observatory pendulum has a very heavy bob, so that they don't have to, they don't need someone to stand there and continually push it back and forth. Okay, so the period does not depend on the mass. One thing that will depend on the mass is the tension in this pendulum bob. The greater the mass is, the more tension you have in the pendulum bob. Okay, so I did want to talk about the uses of this a little bit. Just really briefly, one of the uses is timekeeping. So if you have a pendulum bob, just like a grandfather clock, the pendulum bob and the grandfather clock obeys this equation. So they are keeping time with the period of a simple pendulum. Okay. The other thing is, if you know the length of the pendulum and you know the period, if you can measure the period really precisely, then what you can do is you can use the equation to solve for gravity. Okay? So the simple pendulum is often used to measure gravity. And in fact, if we were in class, that is how we would use the simple pendulum. We would use the simple pendulum, solve this equation for gravity, and we would get something that's like 9.8 meters per second squared. Okay? If you measure period precisely enough, you can even see, because the Earth's gravitational field is approximately constant, but it's not exactly constant for various reasons like land masses and the rotation of the Earth, etc. And if you have a precise enough period measurement, you can actually measure how gravity varies from place to place. So it's a really useful tool in science. All right, class. So that is my lesson for today, and I will see you in the Zoom room. Bye for now.